Today we want to integrate some rational functions. That is a ratio of polynomials. So we'll have a p of x over q of x, where p of x and q of x are polynomials of varying degrees. The way that integrating rational functions is going to work is that we're going to look at our three base cases, and then we're going to use algebra to get to the three base cases. So it's algebra to get to one of our three base cases. That's the way it works. We only need to know, from a calculus standpoint, we only need to know three integrals, and then we use algebra to get ourselves into those three integrals. So here are the three base integrals. I got in the habit a while ago of referring to these as basis integrals, even though from a linear algebra standpoint, it's not like forming a basis. Not in that sense of the word. It's just, this is what we're basing things on. Probably need a better word for that. So there are three basis integrals that we build from. First, we have a constant over a linear factor. So we have a constant over a linear factor. So what that means is that if we have something like 1 over b plus mx dx, and here we just do a substitution, w equals b plus mx. So dw is m times dx, and so we just end up with a 1 over m natural log of the absolute value of b plus mx plus c. That's the first one, where we have a constant over a linear. This is the most straightforward. We did these. So as an example, we don't need an example. We'll do examples later. So number 2. The two that we really need, where we have a constant over a quadratic with linear, sorry, getting my words all mixed up. Good thing I'm recording this. Next case is if we have a constant over a quadratic with complex zeros. So if we have a quadratic, or sorry, a constant over a quadratic with complex zeros, that's going to bring up arctangents. So constant over a quadratic with complex zeros brings arctangents. Then our third base case is where we have a linear over a quadratic with complex zeros. So we have an integral of, let's say, x over a squared plus x squared dx. So when we have a linear over a quadratic with complex zeros, this is going to bring natural logs, just like with the constant over linear. If we up both of those by 1, derivative of the top, the derivative of the bottom is equal to the top, or is a constant multiple of the top. then we'll have a 1/2 natural log of a squared plus x squared plus c. Really, it's these two that we care about. But I wanted to have the constant over a linear. We should also concern ourselves with a constant over a power of a linear. Maybe instead of 3, I should have a 4th. I think I forget to include this one because I just forget to do this one very often. So if we have a constant over a power of a linear, then we'll do a similar substitution, but we're going to read this as, let's say we have b plus mx to the p power. Here's where we add 1 to the exponent and divide by the new exponent. So just because the variable appears in the denominator does not mean that we're going to have natural logs. I see natural log people want to just put a natural log in this one a lot. But we add 1 to the exponent and divide by the new exponent. I also put an m in there. So the exponent is negative p, we add 1 to it, so we get negative p plus 1, which we'll write as 1 minus p. This one comes up a lot less often, for the most part, because I don't think of it very often. And I focus on the algebra getting us to these 3. So, well, that last one is a +1 bonus integral. All right. The next thing that we need is algebra to get us into these cases. So yesterday we introduced these 2 cases, a constant over a quadratic with complex zeros and a linear over a quadratic with complex zeros. If the degree of the numerator is greater than or equal to that of the denominator, we use long division. So let's talk about algebra and when to use it. If the degree of the numerator is greater than or equal to the degree of the denominator, we use long division. That'll make for some thrilling YouTube. Watch dude write sentence silently. That always gets the algorithm going. If the degree of the numerator is greater than or equal to the degree of the denominator, then we use long division. That is, we go from an improper fraction to a mixed number. That's the way I like to think of this, is we go from improper fraction We use long division and we get a mixed number. We take 7/3 and write that as 2 1/3. And we do the same thing with polynomials that we do with numbers. We look at 3, we divide 3 into the 7. We say 3 goes into 7 2 times. 2 times 3 is 6. 7 minus 6 is 1. There's 1 left over. We do the same thing. One of the things that comes up often is what I just said, which is the words that I was programmed with, the incantation that I was programmed with as a child. I was programmed to say 3 goes into 7 2 times. I was never told what that means. I was just told 3 goes into 7 2 times. And so what that means is we can subtract 3 from 7 twice before we go negative. So this 2, the words that we want to update so we can start applying this process to polynomials is, I'm thinking I can subtract 3 from 7 twice before going negative. And so that's what we do. Here we are subtracting 3 twice. That's what that minus 6 is about. Now, when we originally learned this process, we were only dealing with numbers. We hadn't been introduced to polynomials at the time. So we didn't worry about having some language that was portable to other things. We just said, what's the biggest multiple of 3 that's less than 7? And it's kind of ridiculous because in this division problem, it doesn't matter. You don't have to get the 2 correct. You can be way off. You could subtract too many times. You could subtract too few times. You do have to know how to convert your answer to the correct number, the normal way we write the number at the end, so you don't have weird alternate numbers like 1 4/3 or 3 and -2/3. But this is the language that we want. We're trying to subtract 3 from 7 without going negative. That's the whole 3 goes into 7 twice before it goes negative. We also tend to learn this process before we really think about negative numbers. And so we get away with teaching children. I don't know if they still teach children this, but if you're my age, you most likely learn something like, well, you can't take 9 from 7, but you totally can. 7 minus 9 is -2. That's a thing. And for some reason, we keep children from knowing things, which is detrimental to their mental health. Well, their mental mathematical health, let's say. So we need to use long division to rewrite our polynomials, because what we want is the degree of the numerator to be less than that of the denominator. So we want the degree of the numerator to be less, strictly less than that of the denominator. We want the degree of the numerator to be strictly less than that of the denominator, because those are the cases that we have. Constant over quadratic with complex zeros, linear over quadratic with complex zeros, or combination thereof. We want the degree of the numerator to be less than that of the denominator. That is the goal. All right. So let's suppose that we're looking at a rational function. That's the one that I want. So for example, we have, let's suppose we wanted to integrate 2x squared minus 9x plus 7 over x minus 4, the x. In this integral, we see that the degree of the numerator is greater than that of the denominator, greater than or equal to, greater than, but in this case, greater than that of the denominator. So we're going to use long division to rewrite the integrand. So the degree of the numerator So we're going to use long division to rewrite the integrand. So let's do that. So if I take x minus 4 and divide it into 2x squared minus 9x plus 7, the first step is to divide x into 2x squared. We got to think, how many times can we subtract x from 2x squared without going negative? And that is 2x times. I'm going to put the 2x over here in the x column. Then I multiply 2x times x is 2x squared. 2x times negative 4 is negative 8x. And then we subtract. So we get 2x squared minus 2x squared. That cancels out. That always has to happen. Otherwise, we're doing it wrong. We have negative 9x minus a negative 8x is negative 9x plus 8x, which is negative 1x. And then we're still dividing the rest of the polynomial. So I have subtracted x minus 4 2x times from the 2x squared minus 9x plus 7. That leaves minus x plus 7. Now I got to think, how many times can I subtract x from negative x without going negative? And I can do that negative 1 times. Negative 1 times x is negative x. Negative 1 times negative 4 is positive 3. And then we subtract. The question was, how many times can I subtract x minus 4 from 2x minus 2x without going negative? Oh, sorry, x minus 4 from negative x plus 7 without going negative. And I can do that negative 1 times. So let's do that. Let's subtract negative 1 of these negative x plus 3s. The x's cancel by design. 7 minus 3 is 4. And that's the remainder. So now we have rewritten the integrand. There's a whole number part, which is 2x minus 1 And then the fraction part is 4 over x minus 4. Why did -1 times -4 become +3? Arithmetic is not my strong suit, so. I noticed that none of you caught that mistake, so minus 1,000,000 points for everybody. 7 minus 4 is 3, so that's the remainder. So 2x minus 1, the fraction is going to be 3 over x minus 4, so plus 3 over x minus 4. Now I've rewritten the integral, or the integrand. There's a polynomial, that would be like the whole number part, and then there's a fraction, and in the fraction, the degree of the numerator is now less than that of the denominator, which is what we want, because now it looks like one of our 3 base cases. We still got the 2x minus 1. So to integrate that, the integral of 2x is x squared. The integral of -1 is minus x. And the integral of 3 over x minus 4 is 3 times the natural log of the absolute value of x minus 4. From a certain standpoint, this goes back to our original strategy for finding derivatives and finding integrals. If you can write terms, then write terms. The important thing is that we want the degree of the numerator to be less than that of the denominator, and we use long division to get that. Now it's just a matter of practicing our long division technique. Usually what students tell me at this point is they say things like, well, I can do long division with numbers, but I can't remember how to do long division with polynomials. And it's not that you can't remember how to do long division with polynomials, it's that you haven't had practice doing long division on polynomials. If you can divide numbers, but you can't divide polynomials, it's not a matter of, it's a matter of practice. It's not that you don't remember how to divide polynomials, it's that you don't understand what's going on in the long division with the numbers. You're following some program and you don't understand what's happening in the process. To be fair to you, you didn't have to, the teacher didn't require it. I'd be willing to bet that the person that taught you how to do long division on numbers didn't understand the process themselves. They were just given a script to read to you. Ask me how I know. All right. Any questions? A lot of times in math class, in math especially, we conflate proficiency with understanding. And so when kids learn their times tables really fast, we declare them to be good at math. And at this point in my career, I can safely say that kid has not done any math yet. I'll stipulate that they are a whiz at arithmetic, but they haven't really been in a math class. They haven't been challenged mathematically. You know what I mean? So the first thing that we want to establish is our base cases, what to do, what kinds of things we want. We want to remember those 3 base cases, the DVD bonus material, 4 base cases. And then we want to start breaking our, learning what algebra steps we need to take to get into those cases. All right, so one of the things that y'all are going to have to do is learn how to do long division if you don't remember it already. All right, what was next on the list? If you recall yesterday, we looked at the first case where we had a quadratic with complex zeros. In fact, the two big cases that we're dealing with there are quadratics with complex zeros. So we've dealt with denominator is quadratic so that's took care of that. The next case we want to deal with is that the denominator is quadratic with real zeros. That's next step. Next phase, denominator is quadratic with real zeros. And then after that, what if the denominator is more than quadratic? We've also dealt with the degree of the numerator greater than the degree of the denominator. So we took care of that case. We took care of the case where the denominator is quadratic with complex zeros. Now we have to move on to the denominator is quadratic with real zeros, and then we'll look at the denominator is degree greater than 2. Because these last two really kind of are the same thing. Oops, strictly greater than 2. Once we've talked about these 4 categories, then we're done. We can integrate any rational function given time and proper motivation to do so. All right, let's take a look at what happens, what to do if the denominator is quadratic with real zeros. And to do that, we're going to go back, since this is going to be an algebra thing. So to do that, oh, there's one more case here that we'll fill in later. Before we integrate a rational function where the denominator is has real zeros, is quadratic with real zeros, I want you to take a minute. I want you to add these two fractions. Let's suppose that we have 5 over x minus 2 minus, let's go with 4 over x plus 3. So if we add these together, we'll just have 5x plus 3. So 5x plus 15 minus 4x plus 8 all over x squared plus x minus 6. So 5x minus 4x will have is x, and then 15 and 8 is 20 something. So here we are just adding some fractions. All I asked you to do was add fractions. That's what we're doing going this direction. Just add fractions. But if we had to integrate things, I would rather integrate the terms than this one fraction. Notice that the terms is better to integrate than the one fraction. This would be easy to integrate because if we can write terms, then we should write terms. Integrating terms better than integrating this fraction. So our strategy to integrate this fraction, this rational function, is going to be try to write it with terms. We'll notice that the denominator here has real zeros, and that's going to allow us to integrate these terms. So what we need to learn how to do is to learn how to add fractions, but in reverse. And that's a process called partial fraction decomposition. Partial fraction decomposition. This is what we do if we have a denominator that is quadratic with real zeros. We do partial fraction decomposition, PFD. If the degree of the numerator is greater than the degree of the denominator, then it's long division. Quadratic with complex zeros, those are two base cases. If the degree of if the denominator is quadratic with real zeros, then we use partial fraction decomposition. And what we'll find out is that if the denominator is a degree greater than or equal, strictly greater than 2, that is solved with partial fraction decomposition as well. If you're thinking, man, we are certainly in the weeds right now, then you are absolutely correct. If there's a line through calculus of things that we need to know to understand calculus, we have wandered off that line and we are deep in the weeds now. Because the real way we would integrate x plus 3 over x squared plus x minus 6 is to just drop it into Wolfram alpha and say, hey, Wolfram alpha, I have x plus 23 divided by x squared minus x minus 6. What can you tell me about this function? Oh, I had a plus x squared plus x. And it'll totally tell us all kinds of stuff about this particular function, including the partial fraction decomposition. But more importantly, in the case of calculus, it'll tell us what the antiderivative is, or the indefinite integral is. So but that's going to be our next big thing. We're going to have to learn partial fraction decomposition. And the reason that we need partial fraction decomposition is that it's going to, once again, be an algebra trick to help us rewrite an integrand. Because if, for example, I wanted to integrate x plus 23 over x squared plus x minus 6, the technique is to do partial fraction decomposition to rewrite the integrand as 5 over x minus 2 minus 4 over x minus 3, because now I have just base cases. So I'll have 5 natural logs of x minus 2 plus 3. 5 natural logs of absolute value of x minus 2 minus 4 natural log absolute value of x plus 3 plus c. So we've got to pick up this piece. The other reason that I'm doing this is to reinforce our knowledge of polynomials. We knew enough to get by in polynomials, but now we want to know more about polynomials. So we need to remind ourselves of some more polynomial information. Any questions? Comments? Snide remarks? I don't think integrating rational functions is quite as fun as doing trigonometric substitution, but it's still pretty fun. All right, that's going to do it for today. I'll see you all I will see you all on Friday. Tomorrow is some strange working holiday, so I have meetings. I need to find out when those meetings are, but I have meetings tomorrow. So no Zoom meeting tomorrow. I'll see you all on Friday. Don't worry, I'll put an announcement for people that didn't watch the video or weren't here today, because those who weren't here today or won't watch the video between now and tomorrow are legion. All right, that's it for today. I will see you all on Friday. Everybody have a good couple of days, and thanks for playing.